So this first one is labeled theorem 1 in your text. If V1 to VP, those are just vectors in some vector space V. If you take the span of any set of vectors in a vector space, what do you get? A subspace. Yeah. True or false? The 0 vector is a subspace of R3. True. The 0 vector is always a subspace. It satisfies, it is a subset, right? 0, 0, 0 is an element of R3. Okay, so it is a subset. And then it satisfies those 3 additional criteria to be a subspace. The 0 vector's in there. That one's obvious, right? If you add any 2 elements from the set, you land back in the set. Add 0 to 0, you land back at 0. And multiplication by a scalar also keeps you in the set. If I multiply the 0 vector by any scalar, say 5, you get the 0 vector back. So those are the 3 properties for a subspace. 0's in there, it's closed under addition, and closed under scalar multiplication. Okay, so we need to give one reason why the set 1, 2, 3, 4 is not a vector space. It doesn't have the 0 in it, yeah. It's okay that it's only in 1 dimension, yeah. So you could just think of these as vectors that only have 1 entry. Yeah, so there's 10 criteria for being a vector space, right? This fails most of them, right? So the 0 vector's not in there. If you add 3 and 4, right? If I pick any 2 numbers from the set, I'm supposed to land back in the set when I add them. But 3 plus 4 is 7, which is not an element of the set. So it's not closed under addition. Like you said, if you pick a large enough scalar, if I multiply 1, pick an element from the set, any element, by 5, this is my scalar. An element from the set times a scalar, you don't land back in the set. So those are the 3 criteria for a subspace. There's actually 10 criteria for a yeah, it does, particularly for a finite set like this one. Like that really is easy to fail in a finite set. In an infinite set, like all the real numbers, they're a vector space because all of these things actually work. If you look at all the real numbers as a set, 0's in there. If you add any 2 real numbers, you get another real number. You can take a real number and multiply by any scalar you want, and you get a real number back. So the real numbers are a vector space. But if you look at a finite set of them, probably not a vector space. Yeah.
Is it that any vectors added together or all?
If you pick any 2 entries from the set and add them together, the result has to land back in the set. That has to be true for every set of 2 vectors. If it fails for any 2, then you failed that property. That narrows it down also, yeah. Because I can show that this fails in multiple ways, right? 3, 4, I could do 2 plus 3, I could do 2 plus 4. Yeah, right. Yeah. So finite sets of integers are always going to fail. Yeah. A 2-element set where you had 0 and say 7, that would satisfy the addition one, but it wouldn't satisfy the scalar multiple, right? Because if you take a scalar multiple of 7, any scalar, yeah. If the 2 in there was what? Yeah, Yeah. Yep, and we're going to define some spaces that are subsets of, say, R2 or R3, where we let some of the entries be defined by a variable. Yeah. Yep. Good. So there are lots of different things you could have put here for why it fails. Does anyone have something different than these three that you want to check? Okay. Okay, so today we're going to learn about vector spaces and subspaces. R2, R3, and Rn in general, those are specific examples of a more general thing called a vector space. Okay. And a vector space is just a non-empty set V. And remember, a set's just a collection of things, right? It's a non-empty set V whose elements we're going to generically call vectors, but they don't have to be vectors in the form that we've been thinking of them so far in this class, right? We will look at vector spaces whose elements are functions, right? As opposed to just a list of numbers. So this is a generic name, vectors, because all of the vector spaces we've looked at up until this semester, the elements have been vectors. But we can look at sets of other things besides vectors that satisfy all those same properties that Rn satisfies. So it's a set whose elements we will call vectors but aren't necessarily vectors satisfy these 10 axioms. So some of these have special names. Number 1 says that if you have 2 elements in the set V, then U plus V has to also be in the set V for every U and V in the set. And we call that closure. We say that V is closed under addition. And then V has to be commutative and associative under addition. It has to have an identity element under addition, meaning 0 has to be in the set. It has to have additive inverses. For every vector V, there has to be a negative, for every vector U, there has to be a negative U. So that could have been a reason that the set 1, 2, 3, 4 failed, because it didn't have -1, -2, -3, and -4. For each U in the set and real scalar, the product of the scalar and the vector has to also be in the set, closed under scalar multiplication. And then we have 2 different distributive properties, one where you can distribute a scalar to the vectors and one where you can distribute a vector to 2 scalars. And we have an associative property for multiplication, and the multiplicative identity has to hold. 1 times anything has to be that thing. All right, so from these 10 axioms, we can prove a few more facts about a vector space. So the 0 vector is always unique. There aren't 2 zeros in any vector space. For any U, its negative is unique. There's only one thing that you can add to U to make 0. 0 times a vector is 0. C times the 0 vector is the 0 vector. And negative U can be rewritten as -1 times U. So it should feel like, oh yeah, Rn's a vector space. All these things hold. Like we have talked about all of those properties in terms of vectors throughout the semester. We just never listed them all in one place. So, but the set of all cubic polynomials, for example, is also a vector space, because this cubic polynomials all look like ax cubed plus bx squared plus cx plus d. So let's think about some of these properties. If you add 2 cubic polynomials together, is the result another cubic polynomial? Yep. If you take a cubic polynomial and multiply it by a scalar, do you get another cubic polynomial? Yeah. Is there a cubic polynomial that we could think of as 0? Yeah, you could take A, B, and C, and D to all be 0, and that would be the 0 vector. And you actually can go through and say, yeah, all of these things hold by properties of real numbers, because A, B, C, and D are real numbers. Quadratics would also, the set of all quadratic functions would be a vector space. True. In fact, the set of all functions is a vector space. If you have a function f and a function g and you add them together, do you get another function? F plus g is just another function. If you multiply a function f by a scalar, you get another function. We'll take the zero function to be our zero vector, calling them vectors, even though they're not vectors. So all functions also make a vector space. Doubly infinite vectors, I wrote that horizontally. It's also a vector space. So instead of saying R3, we could say R infinity, right? Vectors that go on forever to the left and forever to the right make a vector space. These guys were used in signal sampling, something like that the book talked about. All right, if some set H is a subset of a vector space. So this is confusing, I think. There's the word subset and the word subspace, and they mean different things. Okay? So a subset just means that it's a smaller collection of things from V, right? If H is a subset of V, then it just means grab some of the things in V. That's a new set called H. We call it a subset of V. So if you think in like Venn diagrams, if this is V, you know, H is some smaller set within V. That's a subset. Okay. So if H is a subset of some vector space V, and if H satisfies these three properties, then H is also a vector space, right? And we call it a subspace. So these three properties were the zero vector of V has to also be in H. H has to be closed under vector addition and closed under scalar multiplication. So rather than having to check all 10 properties, you can just check those three if you know that the thing you're looking at is a subset of something you already know is a vector space. Always going to be a zero in that third entry of the vector. Yeah. So yeah, these are some examples of subspaces. So the zero vector is always a subspace. It's in every vector space, so it's a subset, and it's always going to satisfy those three. The set of all polynomials is a subspace of the vector space of all functions. So if we have a vector space of all functions, then all polynomials is a subset of that. Polynomial functions is a subset of all functions, and all polynomial functions would satisfy these three. So it's a subspace. Cubic polynomials is a subspace of the vector space of all polynomials. And all the vectors that have real entries in the first two and zero in the third is a subspace of R3. This is a subset of R3, right? This is a plane in R3, Z equals 0. So this is a subset of R3, some smaller collection of vectors from R3. And the zero vectors in there, if you take A and B to be 0. And if you add any two vectors that look like this, like A, B, 0 to C, D, 0, you're going to get a vector like this, which it has two real entries and then a 0. So this is in the set. Yep. Yep. And then same thing here. You can take any scalar multiple of A, B, 0, and you're going to get another vector that's a real entry, 0. So it also holds under scalar multiplication. Okay, and then finally, this is the thing that was labeled theorem 1. It says for any set of vectors in a vector space, you can take any set. You can take a single vector, you can take two vectors, you could take 50 vectors. For any set of vectors in a vector space, or we could call them elements if they're not actually vectors. Right? For any set of elements in a vector space, the span of those vectors is a subspace, regardless of how many. This is a quick way of proving something's a subspace. If you can show that it's a span of two elements of the vector space. We call that span the subspace spanned or generated by the vectors. And a set of vectors whose span generates a subspace is called a spanning set or a generating set. All right, so let's do a couple of examples here. So we're going to let V be the set of all vectors in R2, right? 2 entry vectors, where the 2 entries are both real numbers, they are both positive, and B has to be smaller than A. Second entry smaller than the first entry. All right, so give me a vector that's going to be in this set. 2, 1, sure. They're both real numbers, they're both positive, and the second entry smaller than the first entry. All right, how about another one? 47, 12. 1, 0. Good. All right. If I pick 2 random vectors from this set and add them together, is the resulting vector in the set, does it satisfy those properties? Real entries, second entry smaller than the first. Yeah. What can you come up with 2? All the entries have to be positive. Yeah, that positive thing makes it hard to do. Yeah, impossible to do. Right, because hmm, hmm. Yeah, that's so. Yeah, we're not going to think about whether this is a vector space just yet, right? So if U and V are in V, is U plus V in V? I think it is. So if I do A, B, right, that's sort of a generic vector from there. Add that to another generic vector from there that also satisfies C and D have to be positive, and D would be smaller than C. If I add those together, my result would be A plus C, B plus D. Is A plus C positive? Is B plus D positive? Yeah, so my 2 entries are positive. Is B plus D going to be smaller than A plus C? Yes, because A and C were both bigger than B and D. So yes, the resulting sum will satisfy all those properties, which means it's in the set. Yep. So it holds, the closure under addition holds. But can we find a specific vector V in the set V and a specific scalar from the real numbers so that when you multiply C times V, you do not get -1. Any negative scalar. Oh, yeah, it's bigger than or equal to A, though, yeah. I was saying smaller, but it's or equal to, yeah. So any negative scalar will make this fail, right? So if I choose a specific vector, like 2, 1, we know that's in the set because we wrote it up here. If I choose my scalar to be, say, -1, right? My resulting vector is going to be -2, -1, which is not an element of V. So that means we just failed one of the criteria to be a vector space. So is V a vector space? No. And what you were just saying, Iris, it has no negatives, right? It has no additive inverses. That would be another reason that it fails to be a vector space. Okay, so here's another set. H is going to be the set of all vectors A that look like A comma B comma 0, right? A, B, 0. So A and B are just real numbers, any real numbers. So list 3 vectors in H. 7, 1, 0. Sorry, Todd, I keep losing what you're saying. Say it again. 2, 1, 0. There we go. That's a good one, yeah. All right, is H a subset of the vector space R3? Yes, every element in H is an element of R3, so it is a smaller set than R3. That's just a yes, right? And there's no special criteria to be a subset. It just has to be contained within all the elements of R3. Is the 0 vector in H? Yes, I just take A and B to be 0. Okay. Is H closed under vector addition? Yes, pick any two vectors in this set and add them together. You're going to get a vector that looks like something, something, 0. So yes. Is H closed under scalar multiplication? Yes. Yes, because take any vector, multiply by a scalar, your entries are going to be a real number, 0. Still in the set. So is H a subspace? Yes, because it satisfied the 3 properties to be a subspace. And R3 we know is a subspace. It's a subset of a vector space, and it satisfies these 3 properties. So yes. All right, one more. Here's a set. It's a set of all 3 entry vectors that look like A, B, 2A plus B. Let's list a couple of vectors in the vector space R3 whose span creates H. 0, 0, what? So let's remember what span means. Span means the set of all linear combinations of, right? So I want 2 vectors that if I take a linear combination, let's say I could use weights A and B, right? A linear combination with weights A and B would give this. So I'll write it out here. I have A times some vector plus B times some other vector. I want that to give me A, B, 2A plus B. Yeah. So to get my A's, I need a 1 in the first entry and a 2 in the third entry here, because this would give me A and 2A. I want a 0 in the middle. So when I multiply this vector by the scalar A, I get A, 0, 2A. And then what vector do I need to multiply B by? 0, 1, 1. And then when I add those together, I would get A, B, 2A plus B. So my vectors whose span is H, right? So the answer to the question is 1, 0, 2 and 0, 1, 1. Those 2 vectors, if you take their span, you create the set H. Okay. Yeah, any multiple of those would also work. Yeah. Yeah, this is not a unique answer. There are other sets of 2 vectors whose span would be H. But the span of these guys is H. Okay. And these 2 elements, 1, 0, 2 and 0, 1, 1, they're part of R3, right? R3 is a vector space. So the theorem 1, says that if you can take the span of 2 elements from a vector space, you always create a subspace. So this set is a subspace of R3 because it can be written as the span of 2 elements from a known vector space. So it's a subspace. And that's how you use theorem 1. All right, you do some problems.